Okay, so we're going to go back and talk about the normal distribution again. Even though we visited it earlier, we're going to revisit it now because it plays a role in the rest of the book. So remember that the normal distribution is a continuous distribution, and it's what people often refer to as a bell curve, sometimes a Gaussian curve. The mean of, if numbers are normally distributed, then the mean is the high spot right there. That's the average, and there is one standard deviation unit on. I got the computer to draw it for me, so it does a better job than I do. I'll remind you that it's defined by a formula, and you're not responsible for the formula, but just to have mentioned it, because at some point later on in the course, I'm going to want to say something doesn't follow the formula, and for that I need to have shown you the formula. Here it is. Okay, so it somehow involves pi and e and all kinds of other stuff. There is mu and there's sigma occurs in the formula. It's centered at, of course, at the mean mu, and its spreadedness is given by the standard deviation here. That distance there is a distance of sigma. And the point about the normal distribution, capital N normal distribution, is that it's absolutely critical for the rest of the book because of the central limit theorem, which we'll talk about, not in this video, but in the next one. The central limit theorem has something to say about samples, and of course the whole course is about samples. So that's why it plays a role in the remainder of what we do. The standard normal curve is a particular instance of the normal distribution. If you take the mean to be 0 and the standard deviation to be 1, you take the mean to be 0 and the standard deviation to be 1, then you get this curve here. So you can see obviously that it's centered at 0, and then the place where the curve changes its concavity there is a distance of 1. Okay, and we'll sometimes find it convenient to use a standard normal curve. We'll sometimes find it convenient to use ones that are not standard, but you'll see it both ways, and so I've covered it both ways so that a person will know what people are talking about. And again, the reminder here. When you look at a normal curve, finding the middle, finding the mean is easy. In this particular, this is a standard normal curve drawn in Stackey. There's a standard normal curve, so the mean is 0, and nobody has trouble finding the mean. How do you find the standard deviation? And the answer is that the curve is shaped like an umbrella in the middle and like a bowl, B-O-W-L, bowl on either side. The technical jargon is concave down, because if you're standing down and look in, it looks like a cave. And the blue is concave up. Concave up. The place where it changes from red to blue, from concave down to concave up, that's called an inflection point. Anyway, the vocabulary doesn't matter. The point is where it changes from red to blue, that distance right there, between the mean and where it changes, that's a standard deviation. So if you're looking at a normal curve, you can by eye pick out pretty well what one standard deviation unit is. And of course, it's the same left and right. The place where it changes from red to blue on the left is also a distance of 1 from the mean. Okay, so you can, by looking at a normal curve, you can make some sense of what you're looking at. You've got a mean and a standard deviation, in this case a mean of 0 and a standard deviation of 1. It's been my experience that most folks in our class won't have taken an IQ test. In fact, often when I ask, I'm the only person who took an IQ test because they were common when I went to school. But the most common IQ test is distributed normally, bell curve, with a mean of 100. A mean of 100, you see here it says mu equals 100, and a standard deviation of 15. And so the curve will look something like this. And what you're looking at is that the great bulk of people are sort of in the middle, but there's a small number of people on the left and a small number of people on the right. Okay, so that's a typical example of data falling on a bell curve. Data can fall however it wants, but some data does fall on a normal curve. An IQ test is an example. And then I want to remind you, all this is remembering. I want to remind you that to work with a standard curve, to work with a normal curve, we standardize the input data. So you take the x data that you have minus mu over sigma, and that gives you the z, and it's the z that you'll use, for example, in Stackey to find an answer. So of course we're going to do some of those. Here we go. We're going to do some now. So there are two ways to do things in Stackey. The first is to just use the numbers as Stackey gives them to us, and that's fine, there's nothing wrong with that. But the second is to standardize, and I'm going to show you both ways because you'll see both ways in practice. Okay, so the Math SAT, a test that most folks in the room are familiar with. The Math SAT is intended to be distributed normally every year. It doesn't come out quite the way intended, but this is a good way to start. Intended to be distributed normally with a mean of 500 and a standard deviation of 100. So mean of 500, most people are supposed to get something like a 500 on the Math SAT, but some people get a little better and some people get a lot better. Not many, some people. Some people get a little worse, some people get a lot worse. Again, not many. Okay, now I can get Stackey to pop up a normal curve with a mean of 500 and a standard deviation of 100. Oops, come to Papa here. There we go. I can get Stackey to give me a normal curve by clicking on normal. And I'm going to ask it for a mean of 500 and a standard deviation of 100. And so mean of 500, and a standard deviation of 100. There we go. You see, when I edit the parameters to get a 500 and a 100, then I am indeed looking at a graph that looks a lot like the picture that I just had on the slide. Mean of 500, standard deviation of 100. And you can see why the SAT people don't want to give anybody less than 200. There are so few people in that zone that they can't really make much sense of that. And same thing above 800. There are so few people in that zone that they figure, what's the difference between an 810 and an 820? It doesn't make any difference. 800 just says you're exceptionally high. 200 says you're exceptionally low. That's all. Okay, so back to the slide here. I'm going to ask some questions about the Math SAT. So I edited Stackey to put in, whoops, it says 600. I typed 600, but it's supposed to be 500. I apologize, a typo. So what's the chance of an SAT score less than 600? So of course I'm going to demo that. What's the chance of an SAT score less than 600? Come on. Having a lot of trouble manipulating my screen here today. Less than 600. So I'm going to click on left tail because I said less than. I don't want less than 304. I want less than 600. So I'm going to enter 600, and hit OK. And there we go. It tells me that if you look at the area from 600 on back, that is 0.841. So about 84% of people will score on the Math SAT 600 or less. Okay, so we can get Stackey to answer all kinds of SAT questions just by sort of entering the numbers and clicking on what we want. Okay, and you can ask less than 300, more than 700, less than 550, etc. I could even ask between 430 and 710. So let me pick some of these, not to do all of them, but just to pick some of them. How about if I say more than 700? Okay, so bring up Stackey. Come on, there we go. Bring up Stackey, and I'll say more than 700. So more than calls for a right tail, and I'll enter 700 down there if I can do it with my fumble fingers. 700, and I find that about 2% of people, a little more than 2% of people, get above 700 on a Math SAT. So not all that many. What is it for 800? I didn't ask that question, but what is it for 800? 800. It's about 1/10 of 1%. So you can see why they don't give you scores higher than 800 because almost nobody gets up there, so they don't feel like they're comfortable saying that they can tell the difference between an 810 and an 820. Okay, one more. What was it was between what? Between 430 and 710. So let me do between 430 and 710 if I can work my thing. So for the right tail, I'll enter 710. 710, and I'll also click on left tail and enter 430. 430. Okay, and Stackey comes up with three numbers: the area less than 430, the area greater than 710, and the area in the middle, 74%. So 74% of people got between a 430 and a 710. All right, so very handy. Stackey's great to use. Absolutely wonderful. Okay, let me go back to the slides. So a person can work out all of these. Now 538, of course, Stackey doesn't know that you can't get a 538 on the SAT. They only give you numbers that end with a 0, but you can still enter the numbers and see what it says. Okay, so all of those involve just entering the data directly into Stackey. What I want to do instead is I want to do the normalized data. I want this to be the standardized data. So I'm going to calculate here women's heights, and I'm going to find sort of the same answers as the math SAT, except I'm going to do them in a slightly different way, just because a person sees them both ways. Okay, so women's heights are distributed normally with an average height of 65 and a standard deviation of 3.5. That's supposed to be in inches. So there we go. You see that characteristic normal curve shape centered at 65. One standard deviation unit is 3.5 inches. Okay, then it says, what's the chance a woman's between 64.5 and 67.5 inches tall? 64.5 and 67.5 inches tall. So I'm going to do this on a piece of paper. If I can get, there we go, the computer to light it up. So I have women's heights are normally distributed with a mean of 65 and a standard deviation of 3.5. And when I drew it, I had a 65 there and a 68.5 and what is that, 61.5. And I got a bell curve. I mean, I'm not a very good curve drawer, that's for sure. Okay, then question one said, I forget what question one said. Question one said between 64.5 and 67.5. Between 64.5 and 67.5. So if I shade that the way Stackey would shade it, I'm looking at 64.5 is something like there, and 67.5 is something like there. So I'm looking for this area right here. Okay, and again, I could type in, I could ask Stackey to give me a normal curve, mean 65, standard deviation 3.5, Stackey be happy to comply, and then I could ask if these numbers, 64.5, 62.5, and get the area in between, just as I did a minute ago, but I'm showing you doing this a slightly different way, just to have shown you both ways, because you see both ways in practice. So here we go. So first, I'm calculating 64.5 minus 65 over 3.5. And that'll tell me the z-score of the left hand of the red area. And then I'll also calculate 67.5 minus 65 over 3.5, and that'll tell me the z-score of the right hand area. So I got a calculator, I'm determined to use it. Let's see here, 64.5, 65 over 3.5, let's see what it says. So 64.5, 64.5 minus 65 equals, divided by 3.5 equals, and I got minus 0.14, minus 0.14. And then for the other one, 67.5, 67.5, well, you can't really see that, can you? 0.5 minus 65 equals, divided by 3.5 equals, and I got 0.71, so 0.71. And now what I'll do with those two z's is I'll enter those into a standard normal curve. So I'm going to pop up Stackey and with a standard normal curve, that is to say with a mean of 0 and a standard deviation, there we go, mean of 0 and a standard deviation of 1, and that's the way it comes up when you just hit the on button. So I'll ask it about minus 0.14. That's the left-hand side, minus 0.14. So minus 0.14. And the right-hand side was positive 0.71. So positive 0.71, 0.71. And Stackey, of course, gives me the three numbers just like it did a minute ago, but it's doing it on a different curve now. It's doing it on the standard curve with a mean of 0 and a standard deviation of 1. And in order to find what numbers to enter down here, I had to standardize. But it wasn't that hard. Okay, and of course I get 444, 239, but more importantly, I got an answer of 0.317. So back to the slide, and the answer to this question is 0.317. Okay, 0.317. What's the chance a woman is more than 6 foot tall? So I'm going to answer that also, just to have done. There we go. Chance a woman is more than 6 foot tall. 6 foot tall, 72 inches tall. Okay, so more than. So again, if you draw the bell curve like so, I'm looking for more than 72, so I'm looking for somehow like so. Okay, so you answer that by normalizing the 72 using the formula. So z equals 72 minus 65 over 3.5. So 72, come on, 72 minus 65 equals, divided by 3.5 equals, and I got 2.00. You can hardly see it, I'm sorry. 2.00, and I'll go back and ask stack key for greater than 2.00 on a standardized curve. Okay, stack key, there we go, and pop it up, and I want to get rid of that. And on the right tail, I want to have 2.00. 2.00. And you see, it's this, we saw this earlier actually, the 2.00. We saw it with the SAT test. It's a little over 2%, just about 2.5%. So that red area is not all that large. Not tiny small, but not all that large. Okay, back to the slides. Back to the slides. Okay, and now, so that 2.3 that we just saw a second ago leads me to my next point. So here's the standard normal curve, mean of 0, standard deviation of 1. So this is the picture that we were just looking at 30 seconds ago. We've often said in class, when we're doing sort of chapter 3, that 95% of the sample data lies within 2 standard deviation units of the mean. And that was a little bit of a white lie. In fact, if you look for what do you have to set the z to in order to get 95, what do you have to set the z to in order to get 95? You actually don't set it to 2 and minus 2. You set it to 1.960 and minus 1.960, and that'll give you 95. So it was a lie, but it wasn't a big lie. The difference between 2 and 1.960 is nothing to stay awake nights about. But nonetheless, strictly speaking, we should have been saying 1.960 when actually we said 2. The 2 was good for back of the envelope. 1.960 is actually perfectly correct. And we're moving into the chapters now, 5, 6, and 7, where we're going to talk about things that are perfectly correct. Okay, now there's a practical class, and in the context of the other approximations that we were making in Chapter 3 and Chapter 4, we didn't worry about the difference between 1.960 and 2. We just didn't stay awake nights worrying about it. But we have, just to have stated the facts, these are the relevant cases. If you want the area to be 0.95, technically it's not 2 and minus 2, it's minus 1.960 and plus 1.960. We call that z star. It's just a traditional name, z with a little superscript asterisk. If you're interested in 0.9 or 0.99, the other numbers that we usually use for confidence intervals, 0.9 was the area between z equals minus 1.645 and z equals plus 1.645. And again, you would call that z star. You would say, for 0.9, I'm using a z star of 1.645. It's just jargon, but of course, having worked with a lot of confidence intervals, we have some sense that you need to have a certain width. How wide? 1.645. If you want to be 95% confident, how wide? 1.960. If you want to be 99% confident, how wide? 2.576. Okay, so the z star there is simply the number that you have to use to get that level of confidence in your confidence intervals. Okay, now there's a topic in these slides here that would be of interest to people who are in education, stay nines, but we're going to happen to pass over it, just a question of trying to keep it manageable. But if you're in education, you might want to have a look. Okay, so very good. So we'll see you for the next slide. Bye-bye.